The idea that Earth held a key place in cosmic affairs was challenged by the Andromeda Galaxy, which significantly altered our understanding of the cosmos. The realization that the Milky Way, our home galaxy, was only one of innumerable others scattered throughout the immense expanse of space was a turning point. We are now able to look farther into space and solve the mysteries of Andromeda because to advancements in observational technology, especially the installation of devices like the James Webb Space Telescope. However, many long-held assumptions about this nearby galaxy have been challenged by recent discoveries based on data collected by the James Webb Telescope. A dim, diffused ring of light spanning the night sky was the dominant perception of the Milky Way more than a century ago. Astronomers' ability to identify individual stars in our galaxy was hampered by this perspective, which was impacted by the limited technological capabilities of the period. Rather, a number of ideas continued to exist, frequently linking the Milky Way to the point of creation, where the sky and Earth met. Our understanding of the Milky Way didn't change significantly until the 17th century, thanks to Galileo Galilei's groundbreaking telescope research. Galileo's discoveries showed that the Milky Way was a vast collection of stars, planets, and other celestial bodies spread out throughout space rather than just a strip of light. In the 18th century, Thomas Wright expanded on Galileo's discoveries by putting out a novel theory that the Milky Way was a flattened disk with our solar system nested inside, rather being a random collection of stars. But Edwin Hubble's findings at the beginning of the 20th century were what really changed the way we view the cosmos. Hubble proved that there were separate galaxies with billions of stars each by identifying far-off nebulae outside the Milky Way using the 100-inch Hooker telescope at the Mount Wilson Observatory. The Andromeda Galaxy, M31, one of the nearest galaxies to our own, was one of these. Records of Andromeda's existence go back hundreds of years, to the 10th century, when the Persian astronomer Abd al-Rahman al-Sufi characterized it as a little cloud. Al-Sufi's acute observational abilities enabled him to recognize Andromeda as a celestial body distinct from the well-known stars that dotted the night sky, even in the absence of telescopic gear. Simon Marius's more thorough description of Andromeda, based on telescopic observations, in 1612 marked the start of serious detailed study of the city. Charles Messier later catalogued Andromeda as M31 in 1764, unintentionally ignoring al-Sufi's prior identification and attributing its discovery exclusively to Marius. When English astronomer William Huggins produced revolutionary observations in 1864 that further clarified the nature of this mysterious galaxy, significant progress was achieved in understanding Andromeda. Every succeeding astronomer added to the expanding corpus of information on Andromeda, resulting in a more sophisticated comprehension of its composition, structure, and position in the universe. Huggins's pioneering measurements of Andromeda's spectrum, which revealed that its spectral signature was different from that of a normal gaseous nebula, were a turning point in our knowledge of this galaxy. Huggins cleared the path for a more thorough investigation into the actual nature of Andromeda. Despite its enormous size, Andromeda is thought to have a mass that is 1 to 2 trillion times that of our Sun. For years, astronomers have been fascinated by this enormous cosmic structure that is located quite close to us in the vast expanse of space. In cosmic perspective, Andromeda is ancient, with an estimated age of 10 billion years, suggesting a rich history of formation and evolution. The idea that Andromeda was created by the merger of multiple smaller proto-galaxies spanning billions of years is an interesting part of its creation story. The magnificent Andromeda Galaxy that we see today was progressively formed as a result of this process, which was fueled by gravity. Galactic mergers are frequent occurrences in the universe and have a major impact on how galaxies develop and change over cosmic timeframes. Astronomers thought Andromeda was much more enormous than our own Milky Way galaxy for a long time. Part of the reason for this misunderstanding was the idea that Andromeda was enormous from Earth. Scientists have revised their estimates of Andromeda's mass, nevertheless, as a result of current study that has caused them to re-evaluate previous assumptions. The difficulties in precisely determining the mass of galaxies are highlighted by the current understanding that the masses of Andromeda and the Milky Way are far closer than previously believed. The actual size of Andromeda, which is roughly 220,000 light-years in diameter, is still up for debate among astronomers. Andromeda is larger than the Milky Way, taking up a significant amount of space. The difficulties in precisely determining a galaxy's mass highlight the difficulties in researching these massive cosmic formations. Galaxies are complex systems, and the distribution and motion of their stars, gas, dust, and dark matter are all closely related to their mass. This calls for exacting analysis and advanced observational methods that were unavailable until the modern era. Andromeda's active galactic nucleus, a highly energetic area at the galaxy's center driven by a supermassive black hole, is one of its most intriguing features. Two locations of concentration where emissions are stronger than in the surrounding areas are among the fascinating features found within Andromeda that have been discovered by observations using sophisticated observatories like the Hubble Space Telescope. These studies enhance our knowledge of galactic nuclei and provide insight into the dynamic processes taking place at the center of Andromeda. With an estimated mass of between 1.1 and 2.3 times 10 to the power of 8 solar masses, or roughly 110 to 230 million times the mass of our Sun, the supermassive black hole at the center of the Andromeda Galaxy exerts tremendous gravitational pull. The evolution and dynamics of galaxies, including our own Milky Way, are significantly influenced by the presence of supermassive black holes, which are thought to be common fixtures in their centers. An accretion disk is created around a supermassive black hole when stuff, such gas and stars, approaches it too closely. A galactic nucleus's luminosity is influenced by the intense radiation it emits at different wavelengths due to the heating of this disk, which is made up of swirling material. Because of the special gravitational interactions between the black hole and the nearby stars, astronomers have seen a brighter point of concentration close to the Andromeda Galaxy's center supermassive black hole. The supermassive black hole in the center of the Andromeda Galaxy pulls on the nearby stars with such force that it affects their orbits. Like the planets in our solar system orbiting the Sun, these stars follow elliptical orbits. Stars accelerate faster and become more densely crowded around the black hole when gravitational forces reach their apex at the perihelion, or moment of closest approach to the black hole. The brighter point of concentration seen in Andromeda's galactic core is a result of this stellar concentration and the radiation it releases. Andromeda is home to a large number of globular clusters, which are dense collections of stars that circle the galactic center, in addition to its supermassive black hole. With an estimated 460 in Andromeda, these clusters provide important information about the galaxy's cosmic past and interactions with other galaxies spanning billions of years. These globular clusters indicate that Andromeda has been actively engaging in galactic cannibalism, consuming stars and other elements from smaller galactic neighbors that are under its gravitational pull. In addition, current observations and analysis suggest that the Andromeda Galaxy may be undergoing a change from a conventional spiral galaxy to a rather uncommon variety called a ring galaxy. Elliptical or circular ring-like structures made up of young, bright blue stars encircling a center region with relatively less luminous matter are the hallmarks of ring galaxies. If verified, this shift would enhance the galaxy's allure and demonstrate how dynamic cosmic evolution is. There are two main types of ring galaxies, O-type and P-type. They are distinguished by their circular or elliptical ring-like features. P-type ring galaxies have more irregular ring morphologies with off-center nuclei, whereas O-type ring galaxies have smooth, regular rings and centrally situated nuclei. Only around 1 in 10,000 galaxies are categorized as ring galaxies, making them uncommon cosmic occurrences. Two primary theories have been put forth by astronomers to explain how ring galaxies develop. First of all, two or more galaxies may collide to generate them. On the other hand, a ring-like structure may occur when a smaller galaxy passes through the core of a larger galaxy. The complex interaction of cosmic dynamics is demonstrated by ring galaxies like as the Cartwheel Galaxy, Galaxy Piram 20264, and AR-147, which are believed to have originated through galactic mergers. Even more fascinating, though, is what is now happening. Scientists believe that the Andromeda and Milky Way galaxies are headed for collision and will eventually combine to form a new supergalaxy. This enormous event has attracted attention from all around the world, leading to amusing nicknames like Milkdromeda and Milkomeda. The implications of this marriage for humanity could be significant, notwithstanding the whimsical nature of these nicknames. As the two galaxies get closer, their powerful gravitational attraction will cause their forms to change, creating tidal interactions in which dust, gas, and stars are drawn between them. The galaxies will eventually collide, resulting in chaos and devastation. Stars, gas clouds, and dust clouds from the two galaxies will interact and mix as the merger process goes on, possibly creating new star clusters and structures inside the merged galaxy. In areas where gas clouds clash, the impact will cause star formation bursts, compress, establishing fresh nurseries for stars. Earth will likewise be significantly impacted by the merging process. Changes in the solar system's environment may have an effect on Earth's climate and weather patterns, which could cause local extinctions, habitat disturbances, and changes in biodiversity. The distribution of vegetation and animal habitats may be impacted by worldwide variations in temperature, precipitation, and meteorological events. Furthermore, Earth's atmosphere, particularly the ozone layer, may be impacted by an increase in cosmic radiation in the intergalactic region. This might have an effect on climate patterns and vital processes for plant and animal life. Thus, the merging of galaxies may have profound effects on earthly life, underscoring the connection between cosmic events and terrestrial ecosystems. Habitats for different species may change or become less favorable as ecosystems and the climate change. For the purposes of reproduction, foraging, and survival, many animal species depend on certain migration patterns. Finding food, water, and appropriate breeding grounds may become difficult if these migration routes and dates are disrupted by shifting habitats and climate. Ecosystem biodiversity may alter as a result of changing habitats and climate. Certain species would flourish in the altered environment, while others might find it difficult to adjust, which could result in local extinctions. There may be more competition for resources and more chances for some species to thrive in the changed environments. Regrettably, changes to migration patterns and habitats can have a domino effect on the ecosystem as a whole, possibly leading to the extinction of particular species from particular habitats or geographical areas. Even while these changes are alarming, it's important to remember that the Milky Way and Andromeda Galaxy won't combine right away. It is estimated that the collision will start in around 4 billion years, and it will take another 2 billion years for the merger process to finish. It is anticipated that our Sun will turn into a red giant by then, making our solar system inhospitable well in advance of the galactic merger. Our evolutionary history will probably differ greatly from that of any descendants of our species or other living forms that may exist in billions of years. With options ranging from ejection into the intergalactic medium to inclusion into the new galactic structure, the future of our solar system within the new supergalaxy is still up in the air. The possibility of habitable planets within the new galaxy structure will depend on how stable it is. Although liquid water is thought to be essential for the emergence and maintenance of life, planetary orbits and environmental conditions may be impacted by interactions between stars and possible gravitational perturbations. Emerging life in the new galaxy would probably adapt to its particular environment, possibly leading to the emergence of novel life forms that are different from those found on Earth. Without major evolutionary modifications, modern humans are unlikely to be able to thrive in this new cosmos. In the end, a number of variables, including as the unique environmental circumstances and the capacity of creatures to adapt to them, will determine the evolution and sustainability of life in the new galaxy. Galaxy mergers highlight the dynamic nature of the universe and the ongoing evolution of life within it, even though they also offer fascinating opportunities for the formation of new kinds of life.